Hello and welcome back to this NPTEL course on advanced plasticity of solid continua. We have been going through the derivations of how to get the material tangent stiffness for thermo-visco-plasticity in a more general context, where there are multiple variables like the rates consist of the plastic strain as well as the hardening variables, the kinematic part of the hardening variables, and the forces are also appearing because of the usual stress plus the generalized forces that appear out of hardening. But since we are mostly interested in also applications wherein the von Mises plasticity also holds, for example, in such cases the flow direction typically does not change. The flow direction is held fixed. That means the NP, which is basically your the del sigma of F, right, that the dNP is 0. Okay, that is typically the case. If we actually use this fact, then our derivation of the material consistent tangent becomes much simpler. Also recall that what we are essentially doing is to find d sigma by d epsilon as my material consistent tangent, right, consistent material tangent algorithm, right. You see, this goes into the the expression for the stiffness. How? Because stiffness becomes integral B transpose this material tangent stiffness B d omega, right. You recall this, right. So essentially what we are doing is that since we saw that, right, that since the hardening force X was proportional to sigma, correct. So basically if we take, and since sigma is proportional to strain, so if we take d sigma by d epsilon, then we essentially get all the stiffness information. Stiffness after all is what? The force, the incremental force per unit incremental deformation, right. So this is exactly that. If it were the case that sigma cannot be written in terms of capital X, the other forces that are appearing in the formulation, then this won't work. You understand? So therefore d sigma by d epsilon contains all the information for us here. Okay? So now let us specialize our discussion for finding the material tangent in the special case of von Mises plasticity. Okay? So where the flow rule has this special form, let us take this form. There are other flow rules also possible. We have discussed several such flow rules. Let us take one of these forms, okay, because we have to proceed with a specific form now. Now this is the equivalent stress Q, okay, which is a function of sigma minus capital X. In this particular case, this capital X is basically the back stress, right. So basically it is the centered sigma. Q is a function of centered sigma, and sigma y alpha is the yield stress, which is a function of alpha. Okay. So let us define the centered sigma as xi, okay, so that we can simply write Q of sigma minus x as Q of xi. So the flow direction is del f by del sigma, which is basically because sigma y is just a function of alpha and not of xi. Therefore I can write del f by del sigma is del q psi by del xi, alright. So similarly I can also write del f by del x because there is a minus sign before x here, you understand. So therefore del f by del x is minus del q psi by del xi. So basically that is nothing but minus np, the negative of the flow direction, right. So both of this information I need, right. So you remember that del f by del x is related to my h, right, in the last lecture. If you have forgotten it, or if you don't recall it properly, then go back and check. Now NP is basically a function of xi. So basically we can write dNP as delta NP by delta xi d xi. I mean, in a general setting when dNP is not 0, okay. We will see when dNP is 0, we will come to that also, okay. That therefore can be written, because d xi based on the definition of xi, we can write d xi as d sigma minus dx. So this is the expression for dNP. Now also recall that from the chain rule we can write these matrices basically, these quantities A and B as in this manner, okay. So del NP by del xi and minus del NP by del xi. You can see that from these expressions, okay. Please follow it, okay. So here we have made use of the fact that this particular fact that my del f by del x is minus NP, right. Del f by del x comes here, you understand, here, okay. Now so I can therefore clearly see from here that B is minus A, right. And so we get a simpler expression here by putting B equal to minus A. So purely in terms of A, it is just A inner product with d sigma minus dx, right. Now recall that in this associative plasticity the normality rule holds, and this stress correction is along the flow direction NP, okay. So the stress correction is all along NP, and the back stress evolves in the same direction, because we saw that del f by del x is minus NP. So basically NP is the only direction in which sigma and x, both these forces change, okay. So basically d sigma and dx are collinear with NP. So d sigma minus dx is some scalar factor, because the whole thing here on the left hand side is infinitesimal. So you have to multiply by a scalar infinitesimal factor dc times NP, right, some infinitesimal scalar factor dc. So now let us put this forcefully, right, that dNP equal to 0. Let us say that even if NP changes direction, its effects are minor, of a higher order. So dNP is 0. In other words, that would mean, right, from here this expression that A NP is 0, okay. Now since NP cannot be 0, so this essentially means that A is 0, okay. And now also from the expression for this M that we found in the last lecture, okay, just go back and check the expression for M. We basically have a very simple expression for M with this simplification. When dNP is 0, we have M is just identity, okay. So M inverse now is simply identity. So therefore this d sigma becomes simple, much simpler. This is the form, this is the C inner product with d epsilon minus this, the plastic correction, all right. But here this d delta lambda comes in, right. So this d delta lambda, as we found in the last lecture, is written in terms of G. This is basically NP, I am sorry, okay. This is dNP inner product with d sigma, okay, and G, recall that the expression for G is this. Now with this, because we need to use this here, okay, so we can therefore write this d sigma this way, okay, by putting this d delta lambda here. Now you see that d sigma appears here too, so put everything, all the factors of d sigma, all the terms involving d sigma on the left hand side, and we simply get this better looking equation than the kind of very complicated forms that we got in the last lecture. Okay, so now call this coefficient matrix as K. All right, script K essentially. Okay, so this is my K. So therefore, if I have to get the solution for d sigma, then I need an inverse of K. You see that d sigma is K inverse inner product with this material coefficient matrix, that is the elasticity tensor written appropriately in a matrix form, inner product with d epsilon. In this particular case, even this matrix times vector, that is also called an inner product. Anything that squeezes an object from a higher order tensor to a lower order tensor, okay, is typically called an inner product. So okay, so this is also an inner product in that sense, but yeah. Okay, so now our objective is to find an easy route to get this K inverse. Now recall one important thing here, that when the plastic flow is active, the stresses, all the stresses including sigma and x, everything, okay, can only change in the direction np, which is fixed in our model, okay, because we have taken d and p equal to 0. That means that the plastic flow cannot take any other direction other than np, right. Plastic flow, I mean the corresponding incremental stresses or the forces cannot take any other direction other than np, and that should be able to. So therefore, K inverse has therefore a simplified representation because of this particular fact, that the changes d sigma can occur only along np. Now if you think of, okay, K to be basically a tensor, a transformation on tensors, because you see K is a function of tensors. This is a tensor, this is a tensor, right. So it is basically a function of tensors. So it is basically a linear transformation on tensors. Then the K inverse is affected only in the direction np, that means along only one tensor np, right. So this is a very important point. So when we need to invert K, this becomes very important, to the extent that we can now do this inverse very rapidly and expeditiously using what is called a rank 1 update. It is also called the Sherman-Morrison-Woodbury type formula, okay. But here remember that the action of K is essentially on tensors, essentially on matrices, okay. So when I say a rank 1 update, it is rank 1 in terms of tensors, it is only in the direction of np, okay. So let us first observe a few basic things. For example, np is a tensor, right. So now you think of the tensor product of two tensors, inner product of that result with x, some x, okay. Then by the definition of this tensor product, we can write this as np inner product with x times np, right. This is how you remember that if a and b are two vectors and c is also another vector, then this is nothing but b dot c a, right. So this is exactly the same thing but written in terms of tensors, okay. So now see that because this is true and your essentially K has this structure np tensor product np with a contraction with c, right. So essentially we see that this whole quantity is something like a rank 1 operator, okay, in the sense that if you apply this to any tensor x, then it maps that tensor to a scalar multiple of the fixed tensor this elasticity matrix inner product NP. That is it. Okay. You understand that, right. So therefore you know we can therefore also write this way. Okay. So just see that. So here we have essentially taking this as the you know the action of this on x. Okay. When you take an inner product of this whole thing with x, then you get basically this is a scalar and this is a tensor. It is just a scalar multiple of the tensor, fixed tensor C inner product NP. So in this particular case, you know, you are interpreting this elasticity tensor as a fourth order tensor. Please remember, otherwise if you forcibly treat it as a matrix, then it becomes a scalar, right. So that does not make much sense. So this is the scenario. Okay. So this is the reason why we can actually define this fixed tensor as this elasticity tensor fourth order inner product with NP gives you a second order tensor, right. And then G is basically a scalar and we can therefore write the operator, you know, the K script K or what, yeah, scripted K as identity plus G is a scalar U inner product NP, not inner product, I am sorry, the tensor product NP. So this is a rank 1 update of the identity, because this is the identity, this is just rank 1 because we have already seen that U is fixed and NP does not change direction, right. So now if you want the inverse of this, okay, then let us write the inverse. I will just explain how the Sherman-Morrison-Woodbury approach works here to get a rank 1 inverse. So let us seek the inverse in the form. Let us assume that there is a scalar factor alpha such that K inverse is I minus alpha times U tensor inner product NP, okay, for some scalar alpha. If that is true, then if I take, so this is my K, so this is my K inverse. So if you apply K on K inverse, you get identity, right. You should get. So alpha must be found in such a way that this whole product becomes an identity, right. So let us apply step by step. This product has two operations. First you operate on a vector or a tensor with this, and then you operate the result with this, right. This is how you operate the whole thing. So apply step by step to an arbitrary tensor x. Okay, so first operate by the right factor on x. Okay, right factor is I minus alpha U inner product NP, and you get this. Okay, then apply on the result x minus alpha U NP inner product x with the left factor to get this, right. So you get after expansion this whole quantity, and this, you know, according to our logic so far, has to be such that this whole thing becomes an identity. Okay. So let us now from here, this factor U appears in several places, right, here and here too, right. So basically factor this. So this same thing, the last quantity, that means this whole thing here becomes equal to this, right. So U comes out as a factor, you have this. Now for identity, so what is the requirement for the identity? Because the whole thing worked on x, right, here this whole thing worked on x, and if this whole coefficient matrix coefficient tensor becomes an identity, then the result is also x, right. So therefore, correct. So therefore, you know, we can say that the other things that you are getting, right, other than x in the process, that means this whole thing, that has to be equal to 0. If that has to be 0, because U is not 0, it is a fixed tensor, so this factor has to be equal to 0, this factor, right. and this is exactly what we have written here. Now we can actually solve for alpha from here. Okay, so it's a simple solution. It's a scalar, right? So basically we write therefore K inverse using this alpha, and it is very simple. It is called the rank 1 update, right, along U, along the tensor U, right. Now we can apply this K inverse to get my d sigma as K inverse C inner product d epsilon, right. So put it in a long form using the expression for K inverse, the rank 1 update based expression for K inverse, and what we get essentially is this, d sigma is this, correct. So the whole thing is a function of sigma only, you see that. So put sigma as a factor, so factor out d sigma and write the factor of d sigma to get this algorithmic tangent, material tangent information, which is basically this. Okay. Now this is possible only when this NP remains fixed, because therefore we could actually do the rank 1 update along that fixed NP. Okay. Basically we defined another tensor U and did this. So once the C ALG is available, then finding the the tangent stiffness is no problem. So for every element you can actually find the tangent stiffness as B transpose C ALG B d sigma, which is basically the where B is basically the strain displacement relationship. Okay, so that matrix, strain displacement matrix. Now also see that when so after you have found this Ke, then you have to assemble and get your entire stiffness and solve it iteratively over every time step, right, to get the final solution. Now let us see basically what we have achieved covers several special cases. One such special case will be rate independent plasticity, that I can get when mu tends to 0. Okay, mu actually is 0, tends to 0, let us say. So when mu tends to 0, then from the expression for G, which we actually had some time back, I do not remember if you recall it, yeah, this is my mu. I have been telling you, but there are some inconsistencies in my notation. So this is a double notation that we have. We are using eta also for mu. Okay, so when mu tends to 0, then you will see from this expression that G tends to here, right, tends to infinity, right, because that mu comes below in the denominator. So therefore if you just take a look at the denominator reduces just to NP C NP. This C is basically the elasticity tensor, right. Now in this sense therefore we recover the rate independent consistent tangent. See, observe that here this quantity NPC in the expression for C algorithm, actually C ALG, this quantity is actually 0, right, the yeah. Okay, so the denominator as this is not 0, I am sorry, I think, yeah. So G tends to infinity, so in that case the denominator, so G tends to infinity, right. So the denominator reduces to just NP. So in this particular case from that C algorithm itself we can recover my rate independent consistent tangent by taking the limit as G tends to infinity. Okay, right. So so the point to note here is that the von Mises plasticity is essentially therefore there is an elastic solution, right. We have already discussed this long back, that the plasticity is basically a constrained elasticity because it remains constrained to the yield surface in the rate independent case, and of course it does other things, it can go outside the yield surface, But von Mises plasticity, even in the case where rate independence is not there, rate dependence is there, it is essentially a rank 1 correction to elasticity. That is a very important point, right. It is always a rank 1 correction to elasticity because of this fixed plastic flow direction. So, it is a very interesting thing, because by actually finding this C algorithm for the thermo-viscoplastic case, or the viscoplastic case in this case, because we did not assume the thermal effects, we not only found C algorithm and the consistent tangent stiffness from there, but we found it also as a special case of rate independent plasticity by letting G to go to infinity. Okay. So, right. So, therefore, you know, this becomes a very important point here. Okay. So, now this concludes this particular lecture. So, we have already, you know, discussed quite a bit so far on the finite element implementation. That means we have found the methods by which we can use the theory of thermo-viscoplasticity into a discretized setup. We can pose it in a discretized setup and linearize the governing you know, the flow rule, etc., the corresponding residuals, in a way so as to extract the material tangent and hence the tangent stiffness information. Okay. So, the consistent tangent discussed so far is purely mechanical. As I said, the thermal effects we did not consider, right. So, the thermal part of the residual we have not considered. But then if we have to consider it, there are two ways. Okay. So, let me make this clear. That is, you can still use this same tangent stiffness, provided your thermal coupling is weak. So, what you do, you solve the mechanical part using this tangent stiffness, whatever we have derived, and then using this updated, you know, mechanical epsilon p, etc., you solve the generalized heat equation. Okay. And then that is it, that is your solution, right. So, you do not really have to find the, you know, strictly coupled tangent stiffness, coupled in both mechanical and thermal parts. Okay. So, that is possible, but if you want, so this is called a staggered approach. Okay. This approach, what I just described briefly, is basically called a staggered approach. You solve the mechanical part separately, assuming that the thermal effects are fixed, that is, your temperature is known from the last available Tn at the last available time, and then, you know, once the mechanical solution is available, then you actually go for the thermal solution, update. But a more strongly coupled thermomechanical case, which is also possible, if this staggered approach will work if the coupling is weak. If it is not, if there is a case for a very strong coupling of the thermal and the mechanical parts, then we need a strongly coupled thermomechanical system, right. So, we will discuss the derivation of this thermomechanical tangent stiffness and the material tangent also, consistent material tangent information, in the next lecture. After that, we will go into the strain gradient theory of plasticity in the small deformation setting. Okay. So, we will close this particular lecture here, and I will see you again back soon in the next lecture. Thank you very much.